Well, this video is for Math 111 for section 3.5. So I did do a video for project 3 and I talked about problem 8 from section 3.5, so I won't cover that in this video, but I will go over some of the other problems. So section 3.5 is mainly about the application of these exponential tail functions. You can have y equals a sub 0 e to the minus kt, and that is useful for the radioactive decay or the medicine in the bloodstream. And then you've got Newton's law of cooling, where you've got this ambient temperature that the graph is approaching, okay? Whereas this one is going down to 0. Okay, so let's look at, so in the problems, the first couple problems are about radioactive decay, so let's go ahead and take a look at those. Let's see here, problem 2. We've got radioactive thorium-234. The half-life here is 25 days. And I'll write half-life there to remind us what we're talking about. And we're using this formula, y, or a of t, is equal to a sub 0 e to the minus kt. So that a sub 0 is just the starting amount, okay? Now the idea for half-life, so there's a formula in the textbook that you can use to calculate the value of k based on the number of days or years and so forth in the half-life. You can memorize that if you'd like. I'm not going to provide that to you on quizzes or tests. If we want to calculate the value of k when we know the half-life, so here's one way to do it. So in the problem, they later tell us that we're starting with 40 grams of the substance. So I'll go back and look at that in a concrete calculation. But for starters, if we're talking about a half-life, we know at t equals 0, we're going to have a sub 0 amount of this thorium-234. Okay? This is telling us that after 25 days, we're going to have half of that. Okay? So we can use that to set up an equation here. We can say 1/2 of a sub 0 is a sub 0 e to the minus k times 25 days, because that's our time now. Okay? All right, so first thing we can do here, divide on both sides by a sub 0. And now we've got 1/2 equals e to the minus 25k. So take natural log on both sides. This will be ln 1/2. On the other side, minus 25k times ln e. And remember that ln e is equal to 1 because e to the first power is e. So ln e is equal to 1. And so it doesn't really become involved in the solution here. So all we have to do now is divide on both sides by negative 25. And k is going to be ln 1/2 divided by negative 25. And that's about 0.0277, let's call it. Okay, so there's one way of approaching that. In the problem, they tell you that we're starting with a 40-gram sample. So we could say y is 40 e to the minus kt. And so then if you wanted to do this half-life calculation, you would just take half of the 40 and give you 20 and put the half-life time in for t here. And when you divide on both sides by the 40, there's your 1/2 on this side, e to the minus 25k on that side. And that's the point we are right here, so the rest of the solution would be the same. Okay, so now we've got a value for k, 0.0277. The negative is part of the formula, and so when we put it in there to work these problems, we're going to have 40 e to the minus 0.0277 times T. All right. How much of a 40-gram sample will remain after 60 days? Well, we've got the formula right here. All we have to do is plug in, let's see, negative 0.0277, plug in 60 days for the T, and that will tell us about 7.6. And I believe this is in grams. Okay, and notice that this is more than 2 half-lives, so after one half-life of 25 days, we'll be down to 20 grams. After another half-life, in 50 days, we'll be down to 10 grams, and then in 60 days, we'll be at 7.6 grams. So that's, finding the values along that curve there. And how long will it take, after how long will only 10 grams of the thorium remain? Well, if you paid attention to what I was just talking about there, let's see, let's set this up. After 2 half-lives, we're going to have 10 grams left, right? Because at T equals 25, we'll have 20, and so at T equals 50, we'll be down to 10. So there's one way of solving it. What if you don't pick up on that? Well, put the 10 in for Y, e to the minus 0.0277t, and then solve. We're going to solve for this t right here. Divide on both sides by 40, e to the 0.0277t, and then we'll take the natural log on both sides. So, ln 0.25 negative 0.0277t times ln e. That ln e is equal to 1. And so all we have to do here is divide on both sides by negative 0.0277. And we'll see, we should get approximately 50. And the reason it's going to be approximate is because this value for k is approximate. So, ln 0.25 divided by minus 0.0277. And we get, just about 50 days. So this one, it happened that this worked out to be perfectly on a half-life. If it's not perfectly on a half-life, then you just set up this solution right here. All right, let's look at problem 4. So we've got a 12 milligram sample of radioactive polonium. So we're going to be talking about Y equals 12e to the minus kt. Okay. And we know that, well, at t equals 0, Y is 12. And at t equals 100, we know that Y is going to be 7.26. There we go. Milligrams. Okay. All right, so there's our setup. The first question says, what's the half-life? Well, to answer that question, we've got to know the value for k, really. So let's take this information and plug it in here. That'll allow us to solve for k. So the y value is going to be 7.26, and the t value is 100. So first thing we're going to do is divide on both sides by 12, and see what that gets us. 7.26 divided by 12, 0.605, okay, e to the minus 100k, and then we take a natural log on both sides. So we get ln 0.605 over on this side negative 100k ln e. ln E is 1, and so we can cross it out. And now we just need to divide on both sides by negative 100. And so that'll give us a good approximation for the value of k. So ln 0.605, and then divide by negative 100. So k is going to be about 0.005. Well, how does that help us? So now we know this. All we have to do is calculate the t for this to get down to 6 milligrams, right? Because that's what the half-life is telling us. How long does it take for half of it to be left? So divide on both sides, and when you're working with a half-life, you're typically going to end up with a 0.5 over there. And then take the natural log on both sides. Negative 0.005t times ln E. ln E is 1. And so all we have to do here is divide on both sides by negative 0.005. And that'll give us the half-life. So ln 1/2 divided by negative 0.005. 138, what are we talking about here? Days. Okay, so t is 138 days. Notice that after 100 days, we have more than half of it left, so it makes sense our half-life should be over 100 days. And then part B, how much of the 12 milligram sample remains after 180 days? So now we just have to calculate 12 e to the minus 0.005 times 180, and that'll give us what's left after 180 days. So 12 e to the negative 0.005 times 180, 4.88, let's say, milligrams. And that makes sense because one half-life has passed, so we're going to be less than half of what we started with. But we haven't quite gotten to 2 half-lives yet, so we won't be down to 3 milligrams. We'll be somewhere around 4.88. All right, so let's see what else we've got here. That's the radioactive half-life problems. Let's take a look at a couple of Newton's law of cooling problems. So Newton's law of cooling has a slightly different relationship because rather than going to 0, what's happening is something is cooling off. Sometimes it'll be heating up, but most often cooling off towards an ambient temperature. And the temperature here is going to be the ambient temperature plus CE to the minus KT. All right, so problem 6, we've got our Newton's law of cooling. We know T equals 0, the body temperature is going to be 98.6. Let's see, the ambient temperature is 60 degrees, so we know that T sub A is going to be 60. And the body has cooled down to 72 degrees after 6 hours. Okay, so all this problem is asking us, what's the value of K? All right, once we find that value of K, we can use that to answer other questions about, what's the temperature of the body at a particular point in time, or when was, basically, frequently what they're wondering is, how long ago was the body at 98.6 degrees? In any event, we know T sub A is 60. And we know at T equals 0, the temperature here is going to be 98.6. So when you put that 0 in there, 0 times negative k is still going to be 0. E to the 0 power is 1. So there's our equation now. All we have to do is subtract 60 on both sides, and that tells us that C is going to be 38.6. All right, so now we've got 60 plus 38.6 e to the minus kt. Now we come back and use this information. The temperature is 72 degrees after 6 hours. So we'll put the 6 in there for T. Let's see. So let's subtract the 60 on both sides. So that's going to be 12. 38.6 e to the minus 6k. And then divide on both sides by 38.6. So over here, let's see, 12 divided by 38.6. 0.311 we'll call it. 0.311 is a pretty good approximation. And then again, if we want to solve for k, take a natural log on both sides. Negative 6k times ln e. ln e is 1, so we don't have to worry about it. And just divide on both sides by negative 6. So, ln 0.311 divided by negative 6. K is going to be approximately 0.19, we'll call it 1947, let's say. And that's all they're asking for in problem 6. All right, let's look at one more problem here. Problem 10. We've got some coffee. Oh, I'll put that back up in a minute. Okay, let's see. All right, so we need this relationship. The temperature is T sub A plus CE to the minus KT. Cup of coffee that is 105 degrees is placed in a freezer with a temperature of 0. So that's our ambient temperature, is 0 degrees Fahrenheit. After 5 minutes, well, first let's say at T equals 0, the temperature of the coffee is 105 degrees. After 5 minutes, the temperature of the coffee is 70 degrees. Find an equation using Newton's law of cooling to represent the temperature, and what will the temperature be in 10 minutes? Okay, first thing I want to say is, some people look at this and say, well, every 5 minutes you lose 35 degrees, so after 10 minutes it'll be down to 35. No, because this is a curved relationship and not a linear relationship. A linear relationship is proportional, so yes, every 10 minutes you're going to lose the same amount on the y-axis. Okay? In a curved relationship, in this 10-minute span, you're going to lose this much on the y-axis. In the next 10-minute span, you're only going to lose that much on the y-axis. Okay? So without doing any calculations at all, I just want to communicate to you how important it is to understand that this is not a proportional or linear relationship, but a curved relationship. Okay? So we need to use the formula or equation that represents this situation. We know the ambient temperature is 0. Okay? And we know at T equals 0, the temperature is 105. Okay? And remember how this works from that last problem. Let's see here. 0 times negative k is still going to be 0. E to the 0 power is 1. C plus 0 is just C. And so what we're really working with here is T is 105 e to the minus kt. All right. Now, to find k, we know that the temperature is going to be 70 degrees after 5 minutes. So here's our equation. Divide on both sides by 105. That is actually going to be 2/3 there. 70 over 105 to the minus 5k. All right. So, and you can call that 0.6 repeating if you want to, but be sure to repeat that 6. Don't just call it 0.6 because that's a different number. All right, so just like we did in those other problems, we're going to use a natural log. Take the natural log on both sides. So now we've got ln 2/3 on one side, minus 5k times ln e. ln e is 1, so we don't have to worry about it. Just divide on both sides by -5. And that'll give us a good approximate value for k. So let's see here, ln 2/3 divided by -5. 0.081, let's see, 081, I think is a good approximation for k. Let's see here, find an equation. Oh, right. So now that we've got our equation, our temperature is 0 plus 105 e to the minus 081t. Okay, so now we want to know what's the temperature going to be in 10 minutes. So there we go. We'll make a calculation, 105 e to the minus 081 times 10, about 46.7 degrees, 46.7 degrees. So notice, when I was talking about proportional reasoning says if you lose 35 degrees in this 5 minutes, then you're going to lose another 35 degrees in the next 10 minutes. That didn't end up happening. In fact, we only lost about 23.3 degrees. Okay? So considerably less. And that's what I was saying, is that in this first 10 minutes, you're going to lose more temperature than you do in the next 10 minutes. Okay? And that's true of how things cool off. Okay, so I think that's it for section 3.5. You can see some of it relates directly to the project, some of it relates indirectly to the project. As always, if you have questions, please let me know. Thanks.